1 second. All right, Nancy, you can start.
Okay, so good morning, everyone. So today I'm going to talk about the paper in iClear, which is the deep symbolic regression requiring mathematical expression from data about risk-seeking policy gradients. So here's the basic outline. Today I'm going to go over. Also, there's another section. Should be just have some results. I forgot to post. Yeah.
Okay.
So I'm basically just gonna go over about the motivation and what is symbolic regression and the methods they use and some experiment results. All right. So I think is the one core challenge for the artificial intelligence is like the discovering the underlying mathematical expressions, describing a data set. That's like the one of the important motivations, and which this is actually the problem of symbolic regression. So here comes like what is symbolic regression. And we're gonna, I'm also gonna talk about like the traditional approaches to symbolic regression versus the deep symbolic regression, which is the main topic we're gonna talk about, like the DSR framework. Okay, so what is symbolic regression? Here's just like a quick definition for symbolic regression, which is the process of identifying mathematical expressions that fit observed output from a black box process. Okay, so and it is a discrete optimization problem generally believed to be an NP hard, sorry. Okay. And now we basically, I just lead a few points, just comparing the traditional approaches to symbolic regression and with the deep symbolic regression.
So the traditional approach is mainly genetic programming.
Yeah,
right?
yes.
Okay.
So I think in the GP based, which is the genetic programming symbolic regression, they just use it's like a population of mathematical expressions is involved using the evolutionary operations, just like the selection or crossover to improve a fitness function.
Mm-hmm. So
yeah,
genetic
so
programming is a special type of evolution algorithm, right?
Yeah, yes.
Okay.
So I think one of the disadvantages of the GP is that it can be effective, but it's also like knowing to scale poorly to larger problems and can exhibit some like sensitivities to hyperparameters.
Okay.
So the learning target is a general representation of the mathematical expressions. So what it looks like.
Sorry, can you repeat your question again?
So the symbolic regression tries to learn a mathematical expressions, right?
Mm-hmm.
And the mathematical expressions, there are a lot of mathematical expressions. How they are fitted into a general representations. Like if you have a differential operator, plus, multiply, minus, something like that. Am I understanding it correctly?
Yeah, you're right. I'm just going to talk about in the
Okay.
next few slides. Yeah.
Oh, okay,
Like
sure.
the whole
Sure.
structure. Yeah.
Yeah, I'm just curious about the embeddings of the mathematical expression.
Yeah. So
usually, I mean, the standard symbolic regression doesn't include differential operators.
Okay.
There are some works that are trying to learn the differential equation from
Okay.
data, like their expression includes the differential operators. We're seeing such kind of works like 2 years ago. But usually you're gonna assume, okay, you have some atomic expressions like sine, cosine, logarithm, and how you're gonna assemble them into a more explainable expression rather than just the neural network. Right? Neural network is also an expression, but it doesn't give you any meaning.
Okay.
Do we have any concrete example? What is a symbolic regression? Could we have some example?
I can just show you the picture. Here's like the expression tree. So basically, it contains a library where we can select all the tokens from the library. Like we can see just plus, minus, multiply, division, and log, sine, cosine. Yeah. And here's our expression tree, which in this case, we're gonna use the pre-order traversal, and it's a binary tree. So for this example, the expression we would get should be sine, where we have a constant x, and divide by log y.
What is x, what is y?
So x, y are just two variables, like the input variables. So their input can be so which are the terminal nodes can be input variables are constants, and internal nodes are just like mathematical operators, like plus, minus, division, and multiplication, and log. And are for those mathematical operators, they can be binary operators or unary operators, which like how many children which like how many children each node has. So like for I think that's why like they keep the uniqueness of the expression tree and the expression. Any question?
So are we trying to fit some data? Like we have an input output data, or what are we trying to do here?
Yeah, so we have so let's say we have like a data set. I'm just gonna write this way. So let's say we have a data set. And then sorry, no, not theta, use y. So if we are given a data set, let's say x, xy, and then we have x belongs to the Rn, and where y belongs to R. And then we just want to just symbolic regression aims to identify a function, which is f from Rn maps to R, where this function would best fit the data set.
Mhm.
And well, this functional form of f, it's like it's a mathematical expression, like probably in this term.
Why do we have y in our expression here?
Y here is another feature, another input feature.
Yeah, it's another variable. Yeah.
Or you can view x and y as x1, y1.
Okay, so it's x1, y1.
Yeah.
Okay.
Yeah, probably. Yeah, I think. Well, yeah, I can just use another variable like x1,
x1,
x2. Yeah.
Okay. That's much more clear.
So I have a question. So by the binary tree, can you make sure all kinds of the expressions can be generated by the binary tree? Or do you have other kinds of trees?
You mean like different?
Yeah.
Oh, you mean like one expression can have like two different trees?
No,
like
I mean
two different like structure.
no, I mean just by the binary tree, you can generate all kinds of the expressions, right?
Yeah.
Okay.
Yeah, I think for
So-
this binary tree is like the I don't know if you guys know that the very old calculator, you cannot enter the entire mathematical expression and just enter the equal. You have to enter the number one by one. It's like a tree. So basically, if you have a tree, I think you can generate any mathematical expression. Yeah.
Yeah, so I think it's the RNN emits and categorical distribution, and we can obtain a token from that distribution, which I can show you guys the picture. Yeah, it's right here. So from the RN emits a categorical distribution where this distribution can we can obtain a token from this distribution, and we just get this token like one by one, and this is the pre-order traversal.
So the token can be operators or constant or input
Yes.
variables.
Yes, so these tokens are chosen from a given library, yeah, what I write here. So I think it's that yeah, so each token has a value within a given library of possible tokens.
I mean, it should also contains the input variable, right? If you have two input variables, it also.
Yeah, it contains like x, like x1, x2, or like y, or
X1, X2,
yeah.
And
Yes.
constant.
Yes. So to be more general. Yep.
And the library itself just defines the operators.
Yes. It's more like a functional operators set where you can choose from the library.
Okay. So they create RNN to they create RNN model to generate the sequence of those tokens.
Yep, exactly.
So the RN takes the output from the previous layer and what's the other input node?
So so for each token, the RN emits the categorical distribution over tokens.
Yeah, right.
And we have a token. Let's say we have this division sample here, and the parent and sibling of the next token are used as the next input. Yeah, are used as the next input to the RN. So like the subsequent tokens are sampled autoregressively until the tree is complete.
Okay, yeah. So how do you determine how many layers in the RN? It's a hyperparameter to preset before the training the algorithm, training the model. Like, how many layers? How to determine how many layers of the RN?
I think it's until you reach the terminal node.
How do you? But for RN, you cannot reach a terminal node, right? So if you give a RN, it always outputs something.
Yeah, I mean, like just for the, I think it's for the simple token itself. If you reach like if you reach like a constant, you cannot have any like you cannot have any children for a constant. So that way, like for the extraction tree itself, it reached the terminal node.
Okay, I will look at that.
Yeah, that's an issue, Nancy. When I just skimmed through that paper, I didn't got clear like how the two things. First, I mean, during the sampling procedure, how do they determine who is parent, who is sibling? It is doable online for the pre-order traversal at any node. You can determine who is the parent, who is sibling.
It's a binary tree. If you restrict it to a binary tree, then you give it a sequence. You have a deterministic. You have already determined a particular structure of that. So if you have a divided operators, yeah.
I mean, this is curious. I have a.
But why they use pre-order traversal? Is how they
they gave the pseudocode to find the sibling and parent as an appendix, and it's doable.
So for any subsequence, like even it's a partial tree, for any node you can determine who is parent, who is sibling.
Yes.
Yeah.
They gave
You will be able to map a pre-order traversal sequence to a unique binary tree.
Yeah.
Okay.
But my question is, for like conventional INN use case, we will have a sequence like from the data set or whatever. But now it seems like we are letting the RN freely generating any sequence. Like our input doesn't contain any sequence. Our input is just a set of XY mapping, right? Instead, we use the RN to purely serve as a sequence generator, but our input doesn't contain any sequence.
That's yeah.
So your input is the training input and training output. It uses RN model to generate a sequence which can be decoded as an expression. You're gonna evaluate how well this expression fit the training inputs and outputs and give you a reward. And then update this model, update this sequence generation model. That's the idea.
And we only have one sequence, or are we like we are optimizing this unique sequence? It's not like
you don't know the sequence actually.
So we try to find one.
You try to find a model to generate the sequence.
I mean, the final sequence will be only one. Our ultimate goal is to find one sequence. Am I?
Yeah. Once this model is given, like suppose I have knowing the parameters of RN, and I can generate. I mean, from probabilistic model, you can still generate a lot of expressions, but you can find the one who has the maximum likelihood.
Then let's say when we have done training and we want to actually show what is the final expression, how do we do?
You just use this RN to you just maximize the likelihood of RN. You use this RN to generate the expression, or you use this you use RN to generate the expression who has the maximum likelihood.
So it should be a unique one.
No, it's not a unique one. Actually, in this paper, they just use the RNN to generate the distribution of the expression, but the final result they returned is the expression that has the highest accuracy. It's only a sample. Yeah, they find the most useful one in all the samples.
Okay, so it's like you use a RNN to generate a lot of sequences, and we select one of them using some other criteria like accuracy or RMSE.
Yeah,
you can view that, but I think it's better to view as a maximum likelihood or maximum probability, maximum posterior probability. So it is a generator. It's a probabilistic generator. Well, you use this data to adjust the parameters of this probabilistic generator. Well, once your model parameters are identified, well, this generator can still give you a bunch of expressions. You just pick up one who is most probable, or who best fit the data, or who has the maximum likelihood. I mean, they have the same meaning.
Like, are there any limitations to the like sequence length and or number of operators, like how many constants are allowed in the sequence?
Yes, there are. So there are constraining the search space. So I think I have that listed. Yeah, it's right here. So I think the expressions like are limited to, I think in their case, they limited to the minimum length would be 4, just to prevent trivial expressions, and a maximum length of 30, just to ensure like the expressions are still trackable.
Okay. And how do they ensure that the generated sequence is a valid binary tree expression? It's not like you randomly generate a sequence, it will be a valid expression.
Yeah, that's a good question. I want to ask this as well.
You mean like how do they check like it's a valid expression?
Yeah, if you're generating a sequence using RNN, it could form a unique binary tree, yes, but it is not necessarily a valid expression. Suppose you have emitted three nodes, constant. It's not a valid expression, right?
Well, I think it's that you mean like suppose like we generate like a constant. Is that what you mean?
Yeah.
I think it's let me see. I think in their case that they know like
they can't
they know
generate
like
such tree because for the first constant node it's already terminated, so they cannot generate.
Yeah, that's right. Yeah, so they know like how many children each node each node has based on its value. Like they know like multiplication is a binary operator, and it can only has 2 children. That's why it can have like 2 branches. But for a constant, it itself is a terminal node, and I think it would just like terminate the expression, well, just end the expression, and that's the expression itself.
It seemed, maybe I'm wrong, but it seemed like in your first slide you mentioned that terminal nodes were variables or constants, and so that would be that would be the definition of a terminal node. Is that so? It wouldn't be the case
Yes.
that a node up from there, yeah, exactly. So
Yes, that's true.
Yeah.
I guess that they have some rules to determine if the tree, when it's done, it is valid or not, right?
Yes. Let me see.
I mean, in their code, there must be some checking mechanism. When they generate such an when the RNN generates an invalid expression, it will resampling or it gives a extremely small reward, like negative infinity or something like that.
Okay, can you go to the RN figure? I want to double check.
This one?
Yeah. Yeah, I think in the first row, all the constant on all the variables are sampled, the RNA is terminated, and you can construct a tree. I think that's their rule.
Can I say it again?
So in the first row, the sample token, when all the constant in the set in the variable set and the operator set, when all the constant and the variables are sampled, then the construction of the tree is terminated. Then we are done with generating the tree.
You can repeat variables and constant. Right?
Yeah, right.
Yeah, you can. Yeah.
The XX, yeah, right.
Yeah, I feel like they should have some specific termination. Otherwise, you can keep generating. Your expression can contain as many x, y constant as you want.
So it's the main generating process, not controlled by the IRM, but actually controlled by a algorithm.
Yeah.
Yeah, you should have some extra control. I mean, you use a probabilistic model to generate an expression. It's a sequence, but the sequence could be valid or invalid. For the invalid case, you either ask your generator to resample, or you give it a big penalty, like a very small reward, negative reward to enforce the generator not generate invalid expression.
Yeah, I feel like there's a outer algorithm or main framework. Say, if the first one, if you generate it is plus, then you will recursively you will need to operand to serve the plus, right? Then you recursively call two generating process, and suppose the left one is a constant, then it's done, and the right one is a plus, then you recursively need another two new expression. Do they have such a hierarchical structure or algorithm to control the generating process?
Nancy, you should look at the code.
Yeah. Let me check.
I mean, you don't need to check right now, but later we're gonna do something upon this framework. We need to know how they ensure the validity of the generated expression. Yeah, they either have some recursive generation procedure to ensure the whole, when you meet the terminal, when you generate terminal token, whatever, it will give you a valid expression, or they have some checking method, like if you generate an invalid expression, what's kind of penalty, or you need to regenerate. I don't know, whatever.
Yeah. Okay, so any other questions so far? Okay. Okay, so and the so as mentioned before, they have they used a reward function to examine like if the expression like how much the current expression fit the data set. And so here's the so for the standard fitness measure in the genetic programming, it's like the what we call like the normalized mean square error.
So sigma y here is the standard deviation of y output.
It's the standard deviation of the target values, sigma y. So here we given a data set like x, y of set n, and we have like a candidate expression. We have a candidate expression f. And just to bound the reward function, they just apply this segregation function right here.
Okay, so the smaller the normalized RMSE, the larger the reward.
Yes.
Okay, they have like the largest reward is just 1.
Mm-hmm.
Okay.
If this equal to 0.
Sure. Okay.
So so for their methods to just train the RN, so use the policy gradients. So they use the reinforcement learning to train the RN to just produce like a better fitting expressions.
Oh, Nancy, what is the architecture of the RN? So it's just a 1 layer neural network or several layers? What's their activity?
I think is several layers.
Did they use any weird architecture? Not weird, like LSTM or simple RN?
I don't think so.
Which RN did they use? Okay, that's fine. You need to double check the detail.
Okay. Yeah, so
The RNA is their policy net, basically.
Is what?
The policy net, the network, policy network. The RNA is.
Policy network. What's the architecture of policy network?
No. I mean, so they try to train the RNA with the reinforcement learning, right? So basically, the RNA is their policy network.
Yeah. What's the architecture of policy network? It's a LSTM, GRN, or whatever.
I don't know. Maybe it's just I think maybe just vanilla. It's just a MLP.
Okay.
I don't think they mentioned the architecture in the paper.
They just say IN.
Yeah, they don't mention the specific architecture of the RN they use.
Okay, then it has to be either SN or GRU. I don't think the vanilla iron will work here.
Yeah, Nancy, this is something they might expose in the paper. So that's why when you check the code, you should look at. They kind of like they won't have the enough space to explain every detail, like how do they ensure the correctness of the generated expressions and also what kind of RNN did they use. But I think in their experiments, they should tell us what is the architecture of the RNN they use. I don't know if how did the reviewers let them to hide the information?
I think in the appendix C, in the paper, for a series descriptions of baseline algorithms, the yeah, I think there they list like a series of baseline algorithms where they have the priority queue training and the vanilla policy gradient as well.
Yeah, but it didn't say what's the architecture of RNN did they use, right?
No, I don't think so.
Yeah, I think the architecture can play an important role here. They said it's including in-situ constraint hierarchical RNN inputs. But hierarchical RNN inputs is what their figure shows, what their graphical illustration of their figure, their model. Yeah, anyway, this should be, you should make it clear when you look at their code.
Yeah, sure.
Well, let's look at their risk-seeking policy gradient. I think Shiboi should take a look at that because they kind of modify the policy gradient.
Yeah, in their appendix, they provide the algorithm for like the title is sampling from an expression from IN. It's
Which section?
Appendix A. I think.
Appendix A.
Okay.
And they do have some cell status. So it should be STM.
They have what?
They initialize on cell status to 0. I believe it's LSTM. In GRU, there's no cell status.
Oh, so that means they use LSTM.
I believe so. Or maybe they abuse the notation like cell status.
Okay.
And algorithm 2 is actually, I think the controlling process as like a recursion. That they are using a outer recursion process to control the generating process.
The algorithm 2, the table.
Yeah, algorithm 2.
Subroutine 2. Okay.
So the algorithm 2, the fifth line is like a recursion. For each node, they will check whether they need any more expression.
Okay, that's good. That's good. Yeah, Nancy, we should figure out their details, like how their algorithm 2 works. If you want to successfully embed our unknown parameter identification procedure.
Yeah. Yes.
Yeah, let us continue. So why not you first introduce the standard policy gradient and explain why they propose the so-called risk-seeking policy gradient.
Yeah, sure. Yeah, I have the standard. Yeah. So here's the standard policy gradient. So we have the G theta, where is the expectation of a reward function just under the expression from the policy. And here's the standard reinforced policy gradient. Just used to be maximize the expectation via gradient ascent. So we have this the gradient of this G standard theta, where is just through the gradient ascent we have this this expectation of the reward function.
Okay, so the standard
this
will be like you can sample n times, right? And big N times. Each time you got the expression, you calculate the reward, multiply the gradient of the log likelihood of that expression with respect to the model parameters. You do the average.
Yes.
So why is it not good?
So I think right here they have like, so for this one is the unbiased estimate. And where I think the main reason is that it exhibit like high variance.
Mhm.
So just in order to reduce this variance, what they usually do is just like subtract like a baseline like function B from the reward. And I think the main reason like they use what they call like the risk-seeking policy gradient is that the mismatch between the objective being optimized and the final performance metric, where the standard policy gradient object like the G STD theta is the expectation, and we want to for this one we just want to optimize the average performance, but where in the symbolic regression we want to find like the best expression, where it becomes like we want to learn only on the maximizing like the best case performance, but not like the average performance.
What is the second statement? What is the meaning of the second statement in this slide? Like,
Oh, you mean like for this point?
yeah. I cannot understand this. Define so the R epsilon theta as the what is the 1 minus R minus epsilon quantile of the distribution. Can you make an example?
Yeah, so
given it's the given the reward of the trajectory is greater or equal to what the R epsilon theta means in this context.
so they define this 1 minus epsilon quantile of the distribution of the rewards under the current policy, where I think this epsilon is like, for epsilon is like the epsilon fraction of samples from the distribution. Just like they want to increase the reward of the top epsilon fraction of samples without like considering like the samples below that threshold.
It's like that, Shibor. So this is a probabilistic generator. So given any policy parameter theta, the expressions you generated is they have a bunch set of expressions that can be generated.
Yeah, right.
So they just want the expressions under your model who has the largest probabilities will also have the largest rewards.
So a subset of
Yeah,
expressions that have rewards that greater to epsilon.
Yeah, they want
Okay.
the reward to, they kind of enforce the reward to the ranking of reward to be consistent with the ranking of their model's probabilities. Otherwise, if you just do the average performance, you can imagine that, okay, I'm gonna, as long as on average I have a very good performance, I have a good reward, that's fine. Right? It is possible that you have many low density expressions who has good rewards, but for high probable expressions whose rewards is worse. But average is still good.
Yeah, so basically in here, they just want to take the expectation over the high rewards expressions, right? Can I say that?
I think so. Yeah.
So given the theta, and you sample a bunch of expressions, but some of them does not satisfy the 1 minus epsilon criteria, and some of them that have satisfy our epsilon theta, and we just want to average over that subset. Okay.
Yeah, they just want to maximize that part of.
Okay. Yeah.
Yeah.
Cool.
Yeah.
Yeah. Okay. Yeah. Cool. I understand. Yeah.
I think that's why they stay like the difference between their standard policy gradient, where they just want to find like the optimized average performance. But for this one, we want to find out, we only want to maximizing what is above the threshold.
Okay.
And right here, they use the sieve sampling, where I think they also I didn't put like the proof and assumptions in the slides, but I think they also attached like their the fully proof in Appendix B. So it's so for this it's a sample MC estimate of the gradient from a bunch of n samples.
So how they calculate the gradient? They're gonna sample an expression, right? And they just look at I mean, if they want to compute the R tau subtracted by R epsilon theta times this gradient, they need to check that R tau is bigger than or equal to. So what's the definition of R epsilon theta again?
So R epsilon theta as the 1 minus epsilon quantile of the distribution of rewards. And the right here, the R, which this is the empirical 1 minus epsilon quantile of the batch of rewards.
How do they get to know that? I know that if you want to, can I go back to the previous slide? Let me take a look. Is of the rewards. Oh, that would be very expensive, right? If you're doing this, R epsilon theta are the distributions of rewards. Right? That means you have to try a lot of expressions, and you kind of approximate. You got, for example, histogram or whatever, and then you pick up the threshold of the rewards.
Yes. And I think right here, where is it? I think let me see.
Okay. Yeah.
Yeah.
Yeah, I think you can check their code, but I don't to me I think they just sample like the regular policy gradient. They just sample their policy and they manually set a threshold, and they just take the subsets that satisfy the threshold and compute the gradient. I don't believe that. So they actually calculate the 1 minus one. You can check how they calculate that.
They actually use the empirical, like R epsilon theta.
Yeah, you have to
from the samples.
Yeah, you have to compute the empirical distribution of R. Right? That means you have to use a current policy to generate a lot of expressions. For each expression, you need to calculate the reward. So you got distribution of the rewards, and then you hit then you know at which reward threshold it is 1 minus epsilon quantile.
Yeah.
And then just
actually,
up.
Actually, after every time you sampling a bunch of samples, you'll get like R epsilon for that batch of samples. So you can just use the empirical value of R epsilon to
but this is
thresholding.
This is really expensive.
Yeah,
like
they just did that in that way. Yeah, I think there is another equation to show this one.
Yeah.
Okay. Okay.
Yeah, they only choose the top epsilon fraction of samples of each batch. Oh, okay. So if you said the batch is 100, then you just choose 100 times epsilon expressions and use them to calculate the gradient, policy gradient.
Yeah. Okay. So any questions so far?
Shibo, did you see a similar type of policy gradient before?
I don't know the risk-seeking policy gradient, but I think there was an old paper called the trust region policy optimization. It's also a technique that only optimizes a subset of the policy. But
that means they just calculate
each time you just optimize a subset that's most promising in the policy space. That's called the trust region. They call it trust region policy optimization.
Okay, so it's actually a special instance of the so-called trust region policy gradient.
I don't know. I'm not very familiar with that paper very well, probably.
Okay.
Yeah.
Okay, so I think what I have for left is their results. So for this table, it's they report the recovery rate comparisons of DSR of their DSR framework and the other 5 baselines.
What do they mean by recovery rate?
So just like how accuracy the recover the expression.
So I mean they run like multiple times and say each time if they can how many like if you run 100 times, if 80 times from your running, you got exact expression.
I think they didn't say like how many like the exact detail, but I think it's that so they just use the recovery as like the exact symbolic equivalence. Like just I think they use like what they call like the SimPy, where I think just like a computer algebra system determine like how like what's the recovery rate.
What's the number? What does the number mean? Like 72% for NGU YN5. What does it mean? Is the recovery rate for a particular expression?
Yes.
So how many data points did they use to train this DSR?
I checked their data, and for I think it was, let me double check. I think it was 20.
20 points?
Like for their yeah, for their data set.
So that means they have 20 pairs of X values and the corresponding function values.
Yes.
And do they add some noises like Gaussian noises?
I think this one for this table they didn't, but for the next they do.
Okay.
So yeah, for this one so for this figure I think this one just a recovery for various ablations of the algorithm 1 across like all the benchmarks. And then for this one is the recovery vs the dataset noise.
What does it mean for no ablation, no risk, no entropy, no constraints?
So I think it's that they did not so they did not like they just compare like if you did not like add any constraints to
that corresponds no constraints, right? But what does it mean for no constraint? No constraint means no minimum length and no maximum length.
Let me see. Yeah, I think is that they test on like the effects of the of those various constraints like on the search space. Like how influence is that?
Yeah, but what does no entropy mean? They never mention entropy in their model.
Yeah, that's right.
They also add a one step entropy maximum reinforcement learning in the final algorithm. So here is the application study for the entropy maximum reinforcement learning.
So what's the meaning of entropy maximum entropy reinforcement learning?
I don't know.
Policy gradient.
I don't know either, but you can see the algorithm table 1, step 10.
algorithm table 1.
Step 10.
You mean the appendix or?
No, just the page 7,
Oh,
on top of page 7.
And in
They just want to reduce the variance of the trajectory. I think they put an extra term into the rewards. Not rewards, not in the directly in the rewards, but it's another objective.
Oh, so
We
G2 hat is just to
reduce the model's variance.
but what does H?
Yeah,
It
it's
is
just like
entropy.
another regulator term.
You sample a bunch of expressions and then just compute the entropy of them and take the gradient of the theta.
Okay.
And you also set a regulator, constant regulator.
Okay, what's their threshold epsilon? Nancy, what's their risk factor epsilon? Do they use the same epsilon across all the experiments, or they kind of test it as well?
I'm not sure yet.
Okay, let us go through the results first.
One more question: what's the score function of their recovering rate? Is there any reference for that? I didn't find that also. So not really familiar with this set.
You mean like
How did you evaluate the sameness of two expressions?
I think they use like they just use like a computer algebra system like called SunPy, like this one.
Okay. Yeah. Okay. All right. I will check that. Very interesting.
I think you can check page 17 for the experimental details.
Oh,
Page,
okay.
Yeah, they have table 2.
So they cross validation. They use cross validation to select epsilon. They said they consider the risk factors epsilon from blah blah blah.
maybe they just use different settings and pick the best values.
Okay. Okay.
Yeah, and I checked for their data folders. I think they did use 20 pairs for all the baseline. So their data set just 20 pairs of XY.
So the noise level is in the middle of your slice. The noise level is the Gaussian noise, the variance of the Gaussian noise to generate the output.
You mean this one?
Yeah.
So right here, I think it's the I think right here they define like the recovery as the exact symbolic equivalence, and the noise they just varied the proportionality constant like from noiseless to 10 to the minus 1.
It's Gaussian noise.
Okay. But what does reward noise mean? I mean, they add some random noise to reward.
I think they just add like a Gaussian to the reward function, like just add like a, yeah.
Okay. What's
So like we have this like our reward function.
why do they check this? Do they want to corrupt the reward as well during the training?
I think this check to show that as like the reward noise increases, like the DSR like still recovers like pretty quickly even for that high.
What does PQT mean? Is PQT a standard?
PQT, that's the priority queue. That's the
I think they want.
That's the priority queue training. So in Appendix C, they describe like the different baseline algorithms.
Yeah, I think the reason they
yeah, you can go first.
Yeah, I think the reason they add noise to the reward function is because they used those risk. What's the name? Risk
seeking.
Risk seeking method. So they want to make the approximation more robust.
But why don't they compare with vanilla policy gradient?
I don't know.
If you want to stress on the advantage of the policy seeking, the risk seeking policy gradient, you should compare with vanilla policy gradient.
You're right.
Okay, what else results do you want to show?
Yeah, and that's just the last one of the so this let me see. So I think the figure A to D is the empirical reward distributions for a baseline.
Mm-hmm.
For one of the benchmarks.
And PG, what does PG mean?
That's the
policy gradient.
Oh, okay, policy gradient. Okay.
yeah, the risk-seeking PG. And they compare the risk-seeking PG with the standard policy gradient.
So this is after training, or this is the policy. No, it's a reward distribution after using different policy gradient.
Yes. And
I'm
the
sorry,
color
what-
bars
what-
here.
What
Yeah,
are
go
those
ahead.
two columns of the figure on the left? The distributions over, it's a reward of what?
You mean the figure B and D?
No, the two left columns of
Oh,
figures, those two figures for two.
You mean the expressions?
No, the left two columns.
Oh, sorry.
Yeah.
This two?
Yeah, you're right. So what's the density means?
Density is
I think
the
it's
reward.
the
It's just the distribution.
density.
rewards, yeah.
Yeah, the density estimate of the rewards for a particular training iteration.
But what does mean? What does the meaning of the full batch and top epsilon batch? If you're running risk-seeking policy gradient, isn't it always using top epsilon batch?
Yeah, I believe so. I'm not sure actually.
Yeah, you need to figure out the details of the experiments. We're not just capturing the overall idea or just the one critical idea. I mean, in a seminar, we're gonna look at every detail. I actually want to know on those experimental results. Some results are really showing it is working. Some results are quite sloppy. Some results just some trick to sell their paper. We need to figure out this.
Actually, the color of the curves corresponds to the training steps. You can see the color bar on the right side. It means the training steps.
Oh, okay.
And the curve itself means the distribution of the rewards. You can treat it as a you can treat it as a histogram of rewards.
So the long tail of the risk-seeking policy gradient means that it's on the right. It means it's better than the standard policy gradient because the standard policy gradient only like the distribution terminates at the 0.6. That means they're contribute. Yeah. Okay. I see.
Yeah, it might improve the rewards much more.
Okay.
Yeah, than the standard policy gradient.
Well, what does full batch and top epsilon batch mean?
I don't know either. They are not very specific about how they get these results.
So ideally, shall we consider like figure B is the best?
Yes.
Yeah, right.
they got, yeah. They got highest rewards in B.
What full batch means and the top epsilon batch means?
I think they in the section characterizing the risk-seeking policy gradient on page 8, they say the mean reward over the full batch is an estimate of the GSTD theta. They just use the estimate of the GSTD theta.
But risk-seeking PG only
Yeah.
only
I know,
works
yeah.
with epsilon batch, right? It cannot do if
Yeah,
if
yeah,
it
so I'm
use a
not-
full batch. It's okay. Yeah.
Yeah, so I'm not sure how they label that as risk-seeking PG, but still use the full batch.
And also, if you do standard PG, how do you do top epsilon batch?
If you do standard PG and epsilon batch, it reduced to it is the risking PG based on my understanding, but I'm not sure. Very clear, but.
Okay, any other results you want to show?
No, that's all.
Okay, any question?
Yeah, I would like ask some question. So actually, I didn't know much about the reinforcement learning. What I'm curious that how to combine it with the RNN. So for the reward, does that mean after predict every talking we have a reward, or that reward is for the final output?
I think that reward is after when you finish generating all the tokens, and you will have a reward, and that measures how the current how the current pre-order traversal that fits the data set. You don't like give a reward for each token.
Okay, so it means that you will search for different combination of the token. So for example, after one step, you get one combination of the token, and then somehow go to another set of the combination, right?
I think it's that they use the reward to keep updating the
So the whole procedure is like that, Xin. So you can imagine, okay, you have your RNN. Every time you use your RNN to generate one expression, which is a sequence.
Mm-hmm.
So they're going to evaluate this expression. The evaluation result is called reward. According to this reward, they're going to update the model who generates this expression. This is an iterative procedure.
Okay, I see. So for one input sample, it will generate many expression and then choose the best one.
It's not necessarily choose the best one. I mean, during the training procedure.
Oh, okay, I see.
And the input, you wouldn't say it's a one input, because every time your data is they're fixed. Like you have 20 input output pairs or 100 input output pairs. Every time, you can imagine you have a machine, right? This machine just give you a bunch of expressions. While you're gonna score those expressions, their score is called rewards. and they're gonna combine those rewards and they're gonna combine those rewards to calculate some gradient, which is called policy gradient, to update the parameters of your RNN. So the
Okay, I
data
see.
here, the training data here is only used to update, to calculate the rewards and then update the model.
The training example is not entered into the RNN. The RNN is used to generate all the expressions, and then you enter the training data into that expressions and get scores, and then you train the RNN back.
Okay,
Yeah.
I see. Yeah, so actually there is a simple question. I think maybe you have discussed this before, so I would like to have a confirmation. So for giving a data set, so the number of the expression, underlying expression in the data set is, I mean, there is only one expression or multiple expression. I mean, for this model, it can figure out any expression or just one expression in the dataset.
I think the goal is to find the best one that fit the data set.
Yeah, so for the dataset, so for the dataset, for the ground, I think there is there only one ground truth expression or multiple ground truth expression?
I think there's only one. There is only one. So you can. So if you have multiple expressions, target expressions to generate, then it reduces to. Then it is a multitask reinforcement learning problem. You can call it a multitask or multi-agent, because you have multiple objectives.
Okay, I see. Yeah. So if so, it means that if I trained on one expression, I mean on the dataset of one expression, it's not easy to generate to another expression, right?
No, if there is a data, like we found some expression which can summarize the relationship between input and output within this data. That's it. Because it's a generated model. It is not conditional on this data, you generate a bunch of expressions.
But you can do transfer learning. If you train on a particular family of expressions, then you can maybe use some techniques to transfer, to speed up, train this RNN policy on another kind of expressions.
Okay, I see. And another question. So in table 1, so in the for the benchmark, for the last benchmark, all the method have the accuracy, recover rate. For the recover rate, all the method have the zero. The zero. So why I didn't get that. Or why this expression is so challenging for all the method, or we can say what's the limitation of the symbolic expression.
Nancy, can you go back to the previous slides, which show the recovery rate? Yeah. Oh, okay. So Xin, you mean that for GP and for Euro core, there are several zero recovery rate, right?
Yeah. So for the last benchmark, the NGU YEN trap. So all the recovery rate are zero. Why this expression is so challenging?
That's a good question. Actually, symbolic regression is a very promising, because the goal is that want to find some meaningful expressions to expression relationships to make your model more interpretable. But if you want to account for that, it is very hard to find such kind of expressions like this x quadratic minus x cubic, I guess, because sometimes a quadratic function is very similar to sine function. If you put the same range like between their first half, the 1/4 period, right? Sine function is very similar to the quadratic function. You can, if you want to fit them, if you use sine to replace quadratic, their RMSE is also very small.
I see.
Yes, it's very hard to exactly recover the original function unless you have like a lot of data. And I'm trying a lot, but even for doing that, because the model regression usually gives you a lot of like local minimum, it doesn't guarantee to give you the exact equation. Sometimes it can give you overcomplicated expressions, and if it is overcomplicated, it's not interpretable at all.
Okay, I see. And actually, I'm also very curious about the value range of the data set. So because in general, in a network, we may need to do some batch normalization, something like that. So what's the range of the input? I mean, yeah. So like what you just mentioned now, maybe the sine function and the quadratic function, I mean the shape are similar. And but if we can have for x, we can have a larger range. Maybe that's not a problem. So I'm curious about the what's the range of the data set? Is that somehow like the x is in the range 0, 1, or -1, 1, between that, or just random? I mean, for the data set itself.
Yeah, Nancy, you should check out their benchmark.
For the benchmark, I think for the data set itself, it seems like it's all between the range from -1 to 1.
Oh, okay, I see.
Yeah.
And another question is that, so as we know that it's possible to use the somehow like use the Fourier transformation to estimate any arbitrary curve. So is that possible for, I mean, because the input range is limited. So is that possible to have some different expression which have exact the same curve, not the exact very close curve? So firstly, is that possible in the data set if it is possible? So can this method to tell the difference of that two expression?
Okay, so you mean that there could be another
yes,
expression also represent the same data set?
Yes.
Yes, and you see that if you use genetic programming, sometimes it gives you a lengthy equation, and after some simplification, it will give you another equation, another expression. So there are actually a problem that once you give an equation, how do you give more simplified form?
Oh, I see.
Yeah.
Okay.
Yeah, there's one business software. It's called Maple, whatever. They can do this very well, but never release their open source. So that's why the people use SymPy. It's an open source library.
Okay, I see.
Like I wonder what's the like any practical usage of such approach, like symbolic regression, and across paper, I feel like the methodology is like search, not they want to search an expression that might be the underlying expression, and they have some limited operators like plus, minus, like a arithmetic operation, and the constants are just some zero one, some chosen one, like -1 and 1, 10, and 1/10. I think the goal is not to approximate the underlying data structure, the underlying data distribution. So what's the usage case of this kind of method?
This is actually quite useful for the engineering, like in NASA or in many other places that they want to find out, like they want to design new parts or design new materials. They're not just wanting you to run a neural network or give SVM to prediction. They want to know the relationship, because like even like you design an airplane, right? You do some experiments. You cannot write down some kind of simplified partial differential equations for that. If you write down all low-level equations, that won't be computationally feasible. So if they want to summarize some formula which can approximately well describe the relationship of the interest. So this is very important, because traditional, I mean, when those people in NASA or GPL, they are not using any machine learning. They actually manually craft those expressions by themselves. They have some of the tables like x squared, x cubic, and logarithm and sine. They want to manually combine those together. Usually, it will start from some linear combination of those equations. See if they can find a curve which kind of get close, fit their experimental data. Then they're gonna keep that secret formula to guide their experimental design. So those are important. I mean, for the like web applications, we do not care about that. But for the traditional engineering domain, they will be very, very important.
Say that they also want to fit some curve or some function, but they want to know what, or they want to get a like an actual expression, not a
actual expression. And when they have such kind of curve, they know, okay, I cannot pick up the material whose properties at this point, because it will make your part crack also, right? You have to choose some property, like they have some materials probably like Young's modulus in between, so that empirically I know that it is on the optimal point on the curve. And this is very important, because those curves are kind of like secret. They're proprietary. It's all the secret things. They find out, they store in their own database. They won't disclose to others.
I see.
And also, there's one interesting application. So actually, the symbolic regression is also used in some insurance company. And they have some like commercial symbolic regression software. And one of our collaborators, they want to use some like a test with some commercial ones. You have to pay for that. And it's very expensive. The insurance company use them to, I don't know how they're going to use them. They might want to evaluate the risk of some clients are doing something, but they choose symbolic regression rather than neural network. They have their own reasons. Yeah, but anyway, this is a kind of promising direction, because all the traditional methods are based on genetic programming or sequential Monte Carlo. That is way too slow. And right now, there's a trend that, okay, we're gonna leverage like reinforcement learning like artificial neural networks to search such kind of expressions, at least I can say it will be much faster than the evolutional based algorithms. And plus, we have some some other interesting problems in a symbolic version. Okay, any other question or comments?
Yeah, I have like I'm thinking about some extension of this application. I mean, the symbolic regression. So I'm curious, what about if there are some hidden variable? I mean, so for the input, it's not just x, y.
Yeah, that's very good.
X1,
that's what Nancy is doing right now.
Oh, okay.
Yeah.
So
because in many I mean in the material science, in mechanical engineering, when they develop some part, they know that the relationship must contain some physical properties like Young's modulus, like a vibration frequency. So your expression should contain these physical quantities to give you some meaningful thing. But unfortunately, you usually cannot give an accurate measurement of that, or it is very costly to give a measurement. Then that requires, okay, I'm gonna come out some expression which not only includes the measured variables, but also includes some latent variables.
Yeah, so
it will serve as the some basic constant.
It's not necessary to be basic constant because they might test a variety of different materials. That means the material properties vary as well. But you just don't know. Like they want to design some part, right? Some part. Well, you can choose different types of steel, right? Different steel has different hardness or different vibration frequency. I don't know that, but I just want some overall performance of that part to reach some criterion, like it can bear with like 100 Newton stress. At the same time, it should be elastic enough. Right? It shouldn't be too stiff, right? And then you can do the experiments, right? You can collect a bunch of different steels, right? And you test their overall stress and elasticity. But maybe it's too expensive to know what's their vibration frequency, what is their other things, right? So only I'm saying, okay, some measurable properties of that piece of material, and also what is your quantity of interest, but you don't know some other hidden properties. But you want to come out an expression which summarize the relationship between the things you feel interested, like elasticity, in terms of the measurements you have made and some hidden properties.
Yeah. Actually, actually, I have another question. So, in the data, I mean, so when I look at the current result table, we can say the input X and Y. So it looks like that the X and Y are just some I mean, not constants. I mean, just have a single value. So what about when X and Y are okay? So maybe what I'm going to ask is that, so for the expressions, if there have some operation on the matrix, so can those method apply? I mean, applied to the operation between matrix, or just for some single value?
In theory, it is. Yeah. In theory, you can do that, but it is even more challenging, right? So right now, I mean, in practical applications, they only have like a few input variables. But even doing so, you can see that recovering the exact equation is quite challenging. If you consider, okay, I have a high dimensional input variables, I have 1,000 input variables, I want to find out expression. I mean, it's not, you can do it, but I don't think this is going to be practically useful.
Yeah, why I ask this, you know, I did a computer vision before, and there are some classic problem in computer vision, especially in the geometry, in the geometry computer vision. So such as how we estimate the transformation matrix or the rotation matrix. I mean, when we do the when we get the 2D from the 3D point, or we do the inverse process, we have the 2D image. How do we recover the 3D thing? So for this, we need to figure out, we need to estimate the transformation matrix or its inverse. So for them, actually, that would be multiplication between the matrix. So that's why I'm very curious, because in that formulation, we need to know some angle around the XYZ axis, and for them we need to calculate the cosine and the sine. Actually, that's exactly the simple combination of the cosine and sine, and with different angle. So for the angle itself, they are unknown, but we know the how the transformation. I mean, we know the function. If we say the angle around XYZ are the variable, so the output, given that, we can know the transformation matrix. So actually, this is a very challenging problem in computer vision. So I'm very curious whether the symbolic regression is a potential method to solve that. So that's why I.
If your input variables are just x1, x, y, and z, maybe you can try that.
Yes.
I think the setting is not the same. Here, you're allowed to use a lot of expressions, sine, cosine, log, and anything. But in CV, like the problem is you need to find out a single matrix with a 9 number or not 9, 27.
12 or 11.
Yeah, and that's much more you only have that single expression. The constraint is you need to transform one point to another point using the same matrix. And here it's like you have several candidate of here the problem is like discrete searching, and in CV the problem is a continuous optimization. The setting is quite different.
Okay, I kind of get your point. Yeah, it's true that in CV, actually we focus on to get the angle around XYZ, and the translation in XYZ direction. So okay,
it's more like an optimization problem. Here it's more like a searching problem.
Actually, we also can formulate that problem into a search problem. It's not
then your solution will be much limited to some discrete value. I don't think that's the ideal for CV use case. For example, you need to set like the angle has to be like 5 degree, 10 degree, and 15 degree. Also, you need to preset some like discretize your angle.
So why I say it's possible to make it to become a certain problem. So for example, if I need to rotate around X for 30 degree, actually it's possible for me to decompose that I rotate around X for 5 degree and then 10 degree and then 10 degree, something like that. So if we have some basic operation, so it's possible to somehow like that. The basic expression is X. So we need to know we operate the X for how many times, and there is a combination. We do the rotation around X for 5 degree, and then rotation around Y for another 5 degree. So with that kind of expression, formulation of that problem, it's possible become a search problem.
But in it, the problem is in that your expression is actually fixed, or your operator is actually fixed. What you need to find is the coefficient. Here, say for the second expression, they have 4 terms. The fourth term, third term, and square term, and 1. The job might become to find the coefficient before all this exponent, not the x, like a, b, c, d, but not to choose whether we need a quadratic term or we need a triple term or linear term, right? In CV, the relationship is fixed. You need to find the coefficient, but here you don't know what's the relationship, and the coefficient is fixed.
So what I'm trying to say is that, so here for the x and y, actually it's possible to define x as some basic operation, like rotate around x for 1 degree, and y is rotate around y for 1 degree, and z is rotate around the z-axis for 1 degree, and then it will become a combination problem.
So you want to use some expression to describe how you do those sequence of rotations?
Yes.
Okay.
Because actually in the CV we also did use some optimization. So somehow like the alternating projection method, they try to approach the target slowly. So I think it's kind of possible to use some reinforcement learning method like here. Yeah, that's just the some possible application for me. Yeah.
Yeah, we can discuss about it offline.
Oh, yeah, sure.
Okay, other comments? Okay, great. Thanks, Nancy, for introducing this paper. So Nancy, do you have a few minutes? I want to chat with you, and for others, I think have a great weekend. So next week we'll have Shibo, Xin, and June. June to present papers.
Yeah, I can do that. Yeah.
Okay, thank you.
Yeah, thanks.
And thank you.
你现在这个课程很忙吗？
哎 ，OK。还好，这2门课。
你现在上的什么课？除了我那个课之外，还有什么？